All right. Well, so we're going to continue our conversation about what happened during early Earth history. And just to remind you, last time we talked about, we finished up kind of the chemical imprint of core formation, and we kind of summarized the whole story of accretion in the early part, how, like, when and how did the core form, when, at what point did the moon form, and then when did the crust start forming. So we just started on the crust, and we're going to talk today totally about the crust, and we'll get through the crust, and then we'll start talking about the atmosphere. And I mean, the short answer to is that all of these things are continually evolving and ongoing. Earth's accretion hasn't stopped. There's still infalling material, but the bulk of it is done, the vast majority. And this is a process, as we talked about last time, that's been happening over time. What's been happening, how much of it's been happening, how much of it is still left on the Earth is, are all components of this. And we have a pretty good picture, but not an entire picture. And the same thing with the atmosphere. It's been changing, as we'll see, pretty substantially relative to the early days, and why we'll talk a little bit about. But today we're going to sort of look specifically. So the first handful of slides are ones that we didn't get to last time. They're still talking about the crust in general. And then we're going to talk about the two kinds of crust, the oceanic crust and the continental crust. And the oceanic crust comes along with something called the depleted mantle. If you recall, I mentioned last time that when we take stuff out of the mantle to make crust, especially early continental crust, the residue of that is what's called the depleted mantle, right? It's the stuff, the part of the mantle that has had crust components removed from it. And that stuff is now what sits in most of the upper part of Earth's mantle, is what's sampled at mid-ocean ridges and that kind of stuff. So we're going to look at those two things. So this, just to start us off, is a rare earth element diagram. We've been talking about the rare earths a lot. Usually these things are plotted with this thing rotated, with the rare earths across the x-axis and this across the y-axis. But this is from a Scientific American article about the continental crust that's highlighted up here from kind of like two of the early big players. And so what I want you to look at is kind of what's plotted here, concentration relative to meteorites, right? And so just like I've been showing you all these other plots, because it's for the general public, they didn't tell you what kind of meteorites these are, but they're C1 chondrites, just like we've been looking at the last couple of times. It's one of the things we always compare stuff to. We compare like, what do we see in a material relative to meteorites? And that's going to tell us something about how it's changed since the Earth originally formed. Another thing that sometimes you'll see stuff relative to is an estimate of what the primitive mantle is, right? If you remember the 90-10 devolatilized de-iron model that we talked about for pyrolite, it has slightly different concentrations. These elements are the refractory elements that don't go into the core and they're not volatile. So their concentrations in a relative sense don't change through those early Earth processes. And that's kind of why we look at the rare earths as a group. There's also a mass variation through them, which you can see here, and a size variation, which means that they behave slightly differently, even though they behave as a group. And as I mentioned last time, the element europium, because of kind of its orbital configuration, is the only one of those elements that takes a slightly different charge. It takes a +2, whereas all these other ones are pretty much always +3. There's some funny business at cerium too, we'll get to next week. But so we pretty much always see a europium anomaly. That's basically, we see smooth trends in the rare earth elements, except a little up or down divot in the europium concentration, and that's simply because it's behaving differently because of its charge. So these are some summaries of what we think average oceanic basalt looks like. These colors are kind of unfortunate, but this one is the oceanic basalt, right? And this is just like an average of thousands of rocks that have been collected from the ocean basins. If you went on to one of the big databases today, you could find almost 20,000 rock samples that you could pull out and take an average and whatever. And then, so that one's got this shape, and all these other ones have the same shape, where they are low at the heavy rare earths and high at the light rare earths. Okay, and so we've got Andesites formed at island arcs. We've got continental basalt. We've got granites formed in the intrusive part at arcs, and we've got early granites from the Archean. Okay, and they all kind of have the same shape. There's some differences, but we call this light rare earth element enriched because the lighter element, which is lanthanum, it goes lanthanum and then it comes across to these guys, are the highest, and the heavy rare earths like ytterbium and lutetium are lowest. Right? They are at lower concentration. And in these particular rock types, there's more than a factor of 100 difference in concentration. Okay, so all of these rocks are similar, except oceanic rocks. And this is because of that thing I mentioned about the depleted mantle. This curve represents volcanic rocks that were taken out of a part of the mantle that already had this other stuff taken out of it. That's why it looks different. We'll get into those details in a moment. But what I kind of want to highlight is that if you look at average sedimentary rocks from around the world, and there are different lithologies we can look at, we'll talk about them in a little bit more detail in a moment, but this is sort of average sediments to see how it looks very similar to the continental rock types here. So the sediments, on average, they have the europium anomaly and they fit in between the curves for these other things. This red one, right, Archean, really old sodium-rich granites, represent a different set of igneous processes and perhaps different conditions that existed way back when we didn't have plate tectonics. And so we get a slightly different pattern. We get a more exaggerated pattern, right? It's more depleted in a relative sense in the heavy rares and more enriched in the light. But if you take your eye away from the red one and just look at this blue, the green, and the black, you'll see that this beige colored band is pretty similar. And we call this a geological average. So sometimes, like if you want to make this average, you have to go into the literature and pull out all these rocks or go into a database. So you have to assume that all of the hundreds or thousands of scientists that collect those rocks collected them equally from everywhere, which they didn't because we go to the interesting places, not the boring places. So sometimes geological averages, when we're looking at average compositions, it's better to just take something that does the averaging for us, right? And the process of making sediments is one of those that produces what's called a geological average. So there's one other thing I kind of want to remind you about, which is during igneous processes, when we do what we call partial melting, meaning we have some solid and we melt it, but not completely, we only melt it a little bit. When we melt it a little bit and we have like a little bit of melt and a lot of bit of solids, we get a process called partitioning. And partitioning is for every element over there in the periodic chart, it decides, do I want to go into that melt or do I want to stay in the solids? And if there's a variety of solids present, like maybe there's some garnet and there's some spinel and there's some pyroxene, some olivine, some elements are going to say, oh, I like that mineral. Other elements are going to say, no, I prefer that mineral. And so this is the whole theory of partitioning behavior of the elements, which we explain with something called a distribution coefficient. I introduced this last time. I'm just going to remind you, it's written just like Henry's law. So sometimes people call it a Henry's law distribution coefficient. But when we're talking about the making of magma, and we're interested in the residue, and we're interested in the magma, and sometimes we use both of those to backtrack back to what the material looked like before it was erected to, we plot the concentration of any element we want, could be lanthanum, could be lutetium, could be, rubidium, whatever, in the solids divided by in the melt, right? And the melt is the thing that comes up, that we sample that then makes volcanic rock, okay? But because the solids isn't one solid, there's a bunch of different minerals, we have to know something about what minerals are present and in what percentage. So that's what modal means. Modal is like a weighted average of each of the solids, okay? And so an element that has a value of this, sometimes what's called a bulk KD, other people just call it a D. It's just a distribution coefficient. If it's low, the value is low, like less than 1, it means there's more of this chemical in the melt than in the solids. We call that incompatible. It doesn't like the solids. Some elements are really incompatible. They completely go into the melt the second it's present. Some elements are really compatible. It's like, unless you melt the whole thing, they are not going into the melt, okay? And then a whole pantheon of elements in between. So if we go back for a second, all of these elements are incompatible in all pretty much all the minerals we can find in the mantle, with a couple of notable exceptions we'll get to later. But this pattern, which if you recall, we know what the pattern is in meteorites, right? We're not showing you that, we're showing you relative to meteorites. So in a primitive mantle, relative to meteorites, these would all be at the same concentration, right? They'd all be at 1 because they all have meteoritic composition because they're refractory elements, as we've talked about in the last couple of lectures. The fact that some of these are higher than that and some of these are lower than that tells us that something happened during the melting process to change them, okay? And that something is the process of partitioning, okay? So if we look in any rocks that come off the mantle and we find patterns relative to meteorites where something is enriched or depleted, we can assume that some process, and generally it's usually thought to be melting or melt migration, something igneous, crystallization. We're going to kind of gory detail on that next week about all the various things that can happen. But for now, we're just looking in a broad sense that the bigger the enrichment or the depletion, we presume it's the larger variation in this value of D, okay? And so when we look at igneous rocks, for instance, we know that for most minerals, rubidium, which has a really low D. It has a really low D because it's a really big honking ion over here. It doesn't fit in the minerals very well because it's big. So because it's big and it doesn't fit in the minerals, it likes to go into the melt. So does niobium, but niobium does it for a different reason. So niobium's over here. It's not that big of an ion, but it carries a lot of charge on it. And so that charge kind of disrupts mineral lattices. So it also prefers to go into the melt. Right? If we were running an experiment in the lab and put a bunch of solids together, we start to heat it up, and then we stop it before it completely melts, and we looked at the concentration, we'd find more of both of these elements in the melt than the solids, because they have Ds of less than 1. But we would find a greater enrichment of this than this, because this D is even more lesser than 1. And like I say, we're going to talk about these Ds in a lot of detail next time. But for now, we're just going to talk about elements as a function of their behavior, whether they're enriched or depleted relative to meteorites, and in various types of rock. So this is a plot showing you the concentration of various chemical elements in the periodic chart and their compatibility. Okay, so compatibility is basically a way of, with the words, saying what I just said here. An element where the concentration in the presence of melt is higher in the solid than in the melt is called compatible, and an element that is higher in the melt than it is in the solids is called incompatible. And it's not binary. It's not like you're one or the other. There could be degrees of it. So you could be really compatible or moderately compatible. You could be really incompatible. You could be or moderately incompatible. So these elements are ordered by their compatibility scale, with the most incompatible, the lowest D over here, and the highest D over here, the most compatible. You see nickel is the most compatible. You really, really have to melt hard to get nickel and cobalt and even magnesium to come out of the igneous, the rocks that exist in the mantle to make igneous rocks. Okay, so now we got 2 curves on here, and I just want you to focus on the purple one for a second. It says continental crust, normalized concentration. And you can see here again, Taylor and McLennan. These are these guys that did an early assessment of continental crust composition. Normalized to chondrites, okay? And so even though it doesn't say it here, it's just telling you that. Most of these diagrams, because geochemists use them all the time, okay, there's a normalization. You always kind of want to know what is the normalization, because it could be other things. But one of the reasons that we normalize, if you think back to when we're talking about the R process and the S process and nucleosynthesis, all these elements are made in that process. Remember, I told you that odd and even isotopes have different abundance variations. They have them in the meteorites, they have them in these rocks. If you normalize, you take out that zigzagginess, right? The odd, even zigzagginess is gone because it's in the thing that we're measuring and the thing that we're normalizing. Okay, so if we look at this pattern, elements organized by their compatibility by like a factor of 100 or 1,000 between these ones here and these ones here, there's a pretty simple pattern, right? The bigger the D, the lower the value, and the higher the D, the bigger the value. Okay, now look at oceanic crust. Oceanic crust that's formed today on Earth. Remember, we talked last time about the difference in the ages The oldest oceanic crust we can find on the planet is about 100, 120 million years old. The oldest igneous rocks we can find on the planet are almost 4 billion years old. So it's a much bigger history there, but the oceanic crust, right, that we can sample, the young stuff, to a first order, it looks exactly the same from this part on. There's like a slight difference here, but not much difference. But over here on this end, this one here goes down, whereas this one goes up. We call this highly incompatible element depleted, because in a relative sense, this thing turns down. Now I'll tell you that geochemists looked at this for a long time and they said, you know what? What if this was formed from the complement to that? Some process happened and made this stuff, right? And as it makes that stuff, it leaves behind a residue that has this signature. And so that's basically, it's an oversimplification what actually happens, but that's an overall pattern what happens. And if you remember back to the Goldschmidt classifications, which we talked about, the incompatible elements, the one on this side, are generally considered the lithophile elements, the ones that like to go into the lithosphere. They don't like to stay in the mantle solids. The siderophile elements, right, they were largely stripped out into the core when we formed the core. So one of the questions that we have, as we talked a little bit about last time, is did the core get formed before the crust or at the same time as the crust? If it was formed at the same time as the crust, we would find more siderophile elements up in the crust because some of the elements in this thing here are also mildly siderophile. Things like niobium, for example. So there are a bunch of different characteristics that are important. There's also the chalcophile elements. We're going to get into those details in coming lectures when we talk about the behavior of the different chemical elements during igneous processes. But for now, I just want you to think about two things on this diagram. One is, where's the number 1? Because that means it's the same as meteorites, right? Anything that's above 1 is officially enriched in that rock relative to meteorites. Anything that is less than 1 is depleted. Because 1 is a ratio, means the same. Okay, so when we look at the elements that are less than 1, there's only a handful of them. Iron, silicon, which we talked about last time when we looked at compositions of different rocks in the mantle. These things only reluctantly go into magmas. They go into magmas, iron as well, but not so much. And so in a net sense, silicon is sort of right here at the turnover point. It's kind of like even Steven, right? You melt some silicate material in the solid earth in the mantle, and some silicon goes into the melt, some stays behind in roughly equal proportion. For these elements that are called compatible, more of it stays behind and goes into the melt. And for these elements, like aluminum, is what we call mildly incompatible. A little bit more of it goes into the melt than the solid, but not that much. It's not even a factor of 2. And then as we go up, we get more and more enrichment because those elements are more and more incompatible. And this slide already sort of highlights that thing I was just saying, that this part of this curve look like mirror images of each other. Okay, so there's also, as I kind of described here, a slight explanation for why these guys right up in here are a little bit higher than those. It's because during the formation of this crust, which we assume the pink stuff was pulled out of mantle that had already had this pink stuff taken out, and I'll show you a model for that in a second. During that first process, this stuff isn't all that incompatible, so it's more left behind. And then the second time we melt it, we actually get a relative enrichment of it because the conditions of melting when we make the oceanic crust are different than the conditions of melting when we make the continental crust. Continental crust is made by taking much smaller amounts of liquid off the mantle. So this slide basically explains the concept of the depleted mantle, and which I've been talking about already, which is that it is mantle that is left behind when we take magma out of it. Okay, and we don't think there's just one depleted composition all around the planet. This is an ongoing process. It always happens. So we have domains of depleted mantle that were made and got depleted a billion years ago, and we got ones that are being depleted today. And they have different compositions because the processes have varied over time. And we will interrogate some of that stuff in a few weeks when we talk about radioactive isotopes, which decay slowly and can tell us about stuff that's happened over that time period. But for today's discussion, we're just going to think about how much of the mantle that was originally there has been depleted. So we're going to think of it as a single reservoir. Now, another important thing that I kind of highlight here is that when we look back on that slide with the abundances, the siderophile elements are low enough relative to chondrites that we think that the core was largely formed before the crust that we can see today, right? When the core was being formed, there was, ton of melting going on. There was an early proto-crust, which we talked about may have been less dense, more like the kind of crust that we find on Mars or Venus, but it's gone, right? It got resubducted and cycled with the rock cycle and all that kind of business. So the crust that we can find today was formed after the core, at least the vast majority. Okay, so this gives us the idea that the simplest way you can think about mantle, right, is we make it, we make the earth, we accrete it, we suck out some core, and then we got this thing that we call the primitive mantle, which is the pyrrolite model. And then we start making crust. We start sucking stuff off, and the crust, the continental style crust, is light enough that it floats up on top, and it's kind of hard to resubduct. So it starts to accumulate, and that leaves behind some mantle underneath it that's been depleted. Then later, plate tectonics starts, and we start ripping open ocean basins, which samples the shallow upper mantle, where the crust has already been removed, and so it's sampling the depleted mantle, and it melts, and it makes oceanic crust. So we get these two kinds of crust, one coming from a more primitive type of mantle, and one from a more depleted type of mantle. Okay, and so this is a model of that process, ultra simplistic, way simpler than it actually is, right? If we think about how the planet works, we know that it isn't a one-way trip, right? It isn't just like we make some mantle, segregate some core, and then make some crust. We got plate tectonics, we're putting stuff back in, right? And the putting stuff back in is also another level of complication, which isn't considered here. But from the just like, we're going to do some bookkeeping here about like how much primitive mantle might be present, or how much of the original inventory of the highly incompatible elements that were in the mantle are now in the crust. We can do a simple model like this, which is to say we start with primitive mantle at a value of 1. The normalized concentration for all these elements is the same as they are in chondrites after this is the pyrrolite model. So this is a 90-10 model where we take 90% of our chondrite and we devolatilize it, we strip out all its iron because that went into the core, and then we add another 10% of chondrite back to it that didn't go through that process. So that stuff would lie on its line because we're normalizing the concentration of a reservoir to that calculated concentration. But then if we start to take out some continental crust, and you can apply a melting model, something that we will talk about again next week. There are different styles, there's different amounts of melt and solid, there's different ways that we can make the solids and melts interact. This is the simplest kind of melting model you can have. It's called batch melting with a melt fraction of 2%, meaning we got a bunch of stuff there, 100% solids, turn up the heat, melt it to 2%, suck that liquid off. It's going to look like this purple line, okay? And that purple line looks a lot like the continental crust line on the last couple of slides where we're looking at it. Now, when we do that, it's going to make a residue in the mantle. The residue in the mantle is going to look like this. This is what's going to be left behind because we stripped all the stuff out from this one line to make the purple stuff. It makes a residual that's depleted. If we later come back to that depleted mantle at some other place in time at a mid-ocean ridge and we melt it again, right? It's going to produce a composition that is increased relative to it. Because even though these things are depleted relative to the original mantle, when we melt it again partially, the concentrations are going to go back up. Okay, so it turns out that to make this curve, the one that matches what we really see, you basically have to take this residual mantle, stick back into it about 10% of the stuff that you would have taken out for this, like left it behind. Think about it like a wet sponge, right? You start to melt the mantle and you extract some melt as a crust. You don't extract it till the mantle is bone dry. You leave some melt behind, just wetting the grains. So if you leave some stuff behind, it kind of re-increases the concentration of these highly incompatible elements, and then you melt that and you make this. And this melt is a 4% melt. That's what F form is. And like I say, you could say, well, why did they pick 2%? Why did they 1% or 10% or whatever? And it's like, because they were just trying to match the pattern that was observed. Okay, and so it's not telling us what the reality was. It's saying that we have scenarios where we can make these two patterns that are not totally far-fetched. They're believable. Whether they happen or not, we don't know, but they're believable. And so this is the observed pattern, and this is the calculated pattern. Now, as I said, we will see is way more complicated than this. But to a first order, you can use these kind of conditions to say, all right, if we started with this and then we made that, and then we got left with some stuff and we made that, how much of each of these things do we think we have on the planet on the basis of some mass balance calculations? So I'm going to go through some mass balance calculations using a really simple element, which is potassium. It's not the most incompatible element, but it's pretty incompatible. And it's a minor element. It's very abundant in the rock, so it's pretty easy to measure. Some of these are hard to measure precisely because their concentrations are so low. So we're going to look at potassium, but we can make these calculations for a bunch of other elements. And we're going to kind of investigate this a little bit more and say, all right, we know the volume of continental crust, and people estimated how that's changed over time. But if we want to look at how much of these elements are in there, how much do we think is left back down in the mantle? How much is in this kind of material? Is there any of this left, et cetera, et cetera? And so this is kind of a summary for the element potassium of how much is in each of the reservoirs of that simple calculation. So the primitive mantle will have a chondrite normalized value of 1, right, for this primitive. The depleted mantle, the stuff that's making oceanic basalts, it's way down here. It's almost at 10%. It's not quite, maybe about 20% of that. Continental crust is way up there. Okay, and so through these calculations, we can calculate how much, what we think the average mantle is. And you can see it hasn't changed by that much. Even though potassium is really incompatible and it likes to go into melts, there's still a lot of potassium down there. And one of the reasons I picked potassium is because along with thorium and uranium, these are the 3 main radioactive heat producing elements in the mantle. Right, so they're part of what's contributing heat that's allowing it to circulate, convect, blah, blah, blah. So we're interested in this guy. We're interested in all 3 of these guys because of that radioactivity, as well as their, they're good elements all on their own. But so when we do these calculations for potassium or rubidium or thorium or uranium or any incompatible element, we come up with a range of values because there's a ton of uncertainties in the calculations I'm going to go through for you. But they tell us that something like 1/4 to 1/3 of the mantle was depleted to make the crust, right? So that would imply that something like 3/4 to 2/3 is just hanging out down there and was not depleted. Problem is we don't find any actual evidence for primitive mantle in the mantle, meaning we don't find any magmas that come up that look like they were formed from primitive mantle. We don't find any xenoliths of primitive mantle. So we think that it's more complicated than that, but to a first order, the main process of making continental crust seems to have distilled melt out of something like 1/4 to 1/3 of the mantle, if that makes sense. And so that the rest of the mantle is not affected. And these are just the concentrations that go into making that, but I'm going to derive them for you on the next few slides. So a couple things we want to know to do this mass balance. One is how much stuff is in the mantle, how much stuff is in the crust. You can do that by volume or you can do it by mass. So this is just a table telling you the mass fraction of the total in each of these inner reservoirs in the earth. What's the mass of the crust? What's the mass of the upper mantle, the transition zone, the lower mantle, and in the outer inner core? Does everyone know what the MOHO is? Okay, the MOHO, the mohorific discontinuity, is basically a change in seismic velocity as you go from the crust into the mantle. There's a big jump in how fast seismic waves, pressure waves vary. These were identified pretty early on in the sort of mid-20th century as a kind of an identifiable layer everywhere. And so you can kind of determine the thickness of the crust. And this is how we kind of know ocean crust is thin and continental crust is thick and how thick continental crust is and so forth. And so igneous petrologists will argue that the MOHO is not actually the exact transition between crust and mantle. It's a complicated set of arguments that I don't want to go through, but to a seismologist, this is how we define the thickness of the layers. And it wouldn't change the calculations by very much because it's, measured in the difference. What we call the petrologic moho and the seismological moho are not all that different in most places. So like I say, and then in the mantle, and I showed you those pictures a couple times ago, we have these transitions that are probably largely driven by mineralogical changes as you go down in the mantle, phase changes with pressure, but also probably reflect some kind of stratification of the mixing pattern. People think that there's areas of the mantle that mix kind of shallowly above this so-called transition zone. That stuff's kind of stirring. They also think that there's some whole mantle convection, like some subductive plates that go down. We can track them because they're cold. They, again, have different seismic velocities. Sometimes you can image them going all the way down close to the core. Some mantle plumes, like the plume that feeds Hawaii, we can see that coming all the way from the core coming up. Okay, so we have two systems. It's kind of like two different gears that are spinning. The upper mantle is kind of spinning quickly, and we're making oceanic crust, and there's a convection system in the shallow mantle, and there's also a deep one. And we know that there are these differences because of the way they propagate seismic waves, and experiments in the lab that tell us we have different minerals in those places that basically divide up the mantle into various things. And I think most people would make the argument that most of the volcanism that we see is happening by melting in the shallow mantle. And if we're making depleted mantle, it's probably up there at the top. Now, there have been people who have tried to argue that depleted mantles in different places. And it's very hard to make that case, especially in a mantle that's circulating. So in any event, if I take the sum of all these mantle zones, we're gonna ignore the core because we're not talking about Cephalopolis. We're just gonna compare the crust of the mantle. We take the mass of the mantle and the mass of all three of these zones in the crust and all three of these zones in the mantle. This is what they look like, right? So 2.4 times 10 to the 25th grams are in the crust, and 407 times 10 to the 25th grams are in the mantle. So this is the crust a tiny percentage by mass, way less than this value, right? So that tells us that as we're making crust, we're stripping out our potassium really effectively. It's just that there's still a lot more crust that could be made from the mantle, right? If we look at the volumes of stuff or the masses, okay? So I'm going to do a couple of calculations here that I encourage you to look at these slides because me talking at you about calculations are not necessarily as easy as following through them carefully what the calculations are. But here's some stuff about where potassium is. There's way more of it in the continental crust than the oceanic crust. You can get that from that diagram with the pink and the purple curves. And there's pretty much no potassium in the core, right? And we can estimate the potassium that's in the primitive mantle, right, from the chondritic model. And we can use the mass of the crust and the mass of the mantle, which is just from that preceding slide, to calculate a potassium inventory in each of those reservoirs, right? So the potassium concentration that we calculate from the pyrolite model is 180 parts per million, which written in percent is 0.018%. That's its concentration before we start making crust, but after we've made it core. Now, if we convert that into mass units, we're just going to multiply it by the mass of the mantle, the primitive mantle, before we extract any crust, we get a mass of potassium, right? It's almost like Avogadro's number, 7.37 times 10 to the 23rd grams of potassium in this primitive mantle. Now, if we look at the average continental crust, right? We look at the potassium concentration, it's 9,100 parts per million on average, which is 0.91%. If we multiply that by the mass of the continental crust, we come up with another number, 1.55 times 10 to the 23rd. Right, so just ignore the 10 to the 23rd. It's sort of like, what fraction of 7.37 is 1.55, right? And that's what it comes out to be, about 20% or so for potassium. And different elements, like I say, come out with different values. And there's a little bit more potassium that's in the oceanic crust. But this gives you an idea that even though the continental crust is a tiny fraction of the mass of the Earth, is a big fraction of the incompatible element load, which is part of how we know that when the melting happened to make that stuff, it was a really small percentage of melting. The smaller the percentage melting, the more enrichment we get in our incompatible elements, because they go into the melt regardless. And then as we add more melt, it just dilutes their concentration. Okay, so we can also make a calculation for the depleted mantle, right? And, oh, excuse me, go one more slide forward. And in the depleted mantle, we also have, you know, an average concentration, which we can multiply out to get a mass. And what we find is that, you know, the amount of potassium is in the oceanic crust is about 1% of the total, and the mass of the potassium that's in the continental crust about 20%. So you add them together, you get 21%. Okay, and again, these numbers are only as good as all the estimates that go into them, including what is the average concentration, right? And so different people come up with different numbers, and that's why we get a range for these things. But they're always in this kind of pocket between a fifth and a third, or a quarter and a third, or whatever. And so the implication, for instance, for potassium is that the bulk of it is still in the mantle, right? We got this crust, it's super rich in potassium, got a lot of it, but there's still a lot of potassium back down in the mantle, which is partly what's helping to cause the, you know, the heating of the mantle by radioactive decay. Okay, whereas oceanic crust has a lot less of the total potassium. Okay, but what's interesting about this calculation is that it allows us to estimate on the basis of potassium and any other element we want, not only the fraction of the element that's in the crust, the continental crust, but the amount that must have been in the depleted mantle left behind, right? Because you can imagine two scenarios. One is you take crust by processing the entire mantle, you're stripping out stuff from everywhere. The other possibility is, nope, you're stripping it out of a part of the mantle and you're leaving the rest behind. Okay, and that has implications for what the depleted mantle is. The smaller the volume of mantle that we use to extract the crust from, the more depleted it gets, because we're leaving behind a bunch of stuff that is undepleted. Whereas if we extract our melt from a big volume, then on average, everything gets a little bit depleted, but not as much. So we use the concentration of potassium in mid-ocean ridge basalts, and you know all the other incompatible elements too, because they are sampling the depleted mantle. We know that. We know that from this modeling from here. We know that from various radiogenic isotope lines of evidence that we're going to talk about. Oh, sorry. And so we can take the concentration of potassium in morbs and compare it to various scenarios for volumes of the mantle and how much we think that mid-ocean ridge basalts on average represent probably something like 10% of melting of the mantle. There are places where there could be more or less. It's a kind of again, a broad sweeping average. So if we know that the oceanic crust today has 400 ppm, this is something that we can measure from our database of average of rocks, then the mantle it came from probably has something like 10 times less than it. Okay, and so when we can compare this 40 ppm concentration value to the primitive mantle concentration value, and that's how we calculate a volume of mantle that was depleted. And the part of the mantle that was depleted is pretty small, right? Again, it depends on the problem is we've been adding stuff back into the mantle, so make some adjustments, but it's measured in handfuls of percent. It's sitting up there at the top. It's handfuls of percent. Okay, so you know, basically, this just kind of summarizes what I just said, which is that you know the continental crust probably came from about 30% of the mantle. I've just taken the average of a bunch of different stuff and left behind a residual that of which some fraction of it is still there, but it's also continually being formed, and some fraction of it has subsequently been changed by adding stuff back into it through the subduction process. But that's basically crust and mantle. And like I said, we're going to come back to the details of how do you melt and what do you get from it and why do you see these kind of rocks in this place or that place, or et cetera, et cetera. But now what I want to do is look at a little more detail at continental crust. Okay, the oceanic crust is complicated, but continental crust is even more complicated. So we know continental crust has a bunch of different types of rock in it, right? And it's hard to say what is average crust, right? Because it varies from place to place. And if you've done any sort of, you know, hiking in the mountains in various places on the mainland, you know, there are some places that are all granite, some places that are like sandstones and whatever, some places that are metamorphic rocks. They didn't all form in one place in one time. There's an aggregate of processes, okay? And some of that stuff happens up in the crust, some of it happened during the process of initial formation. This is just a summary of the different kinds of rocks that we find in, these are igneous rocks, so these don't include any of the sedimentary or metamorphic rocks. But what you will find on this side of the table, and over here we've got the sediments, that the majority of the kind of igneous rocks, ones that not necessarily ones that were erupted at the surface, ones that are intrusive and that cooled slowly, break down into these categories. Something like 3/4 of them are granites or granodiorites, which are high silicon rocks and low iron magnesium rocks, and something much less, are what we call mafic rocks. Similar in composition, major element composition to what we find in the oceanic crust, higher temperature, lower temperature. So there's a process that goes on. And if we were to make the same table for the oceanic crust, it would be 99% this stuff. There's like maybe 1% of these other things that we find very rarely in the oceanic crust. So the things that happen when we're doing that melting to make the two kinds of crust are really different. That's why one of them is dense and sits low, and the oceans fill into those spots, and one of them is less dense and sits high, as we talked about last time. Okay, and then so that's one of the things that makes up the difference. And then when we look at the sedimentary rocks, which form from either breaking down and grinding of these rocks, or things that happen because of the interaction with water, such as the making of evaporite sediments, as we've talked about before, or the precipitation of carbonates. But amongst those types of rocks, the sedimentary rocks, the most common thing are shales. Okay, shales are fine-grained, clay and mica-rich lithologies that are formed by pulverizing other kinds of rock, transporting grains a really long distance. So some of the bigger, heavier grains are left behind, and depositing them in an oceanic basin. So these are marine rocks that represent the stuff that's shed off the continents, and they are thought to give us a pretty good, what we call geological average, right? Because if you go off the coast of California and you collect a bunch of sediments that are going to become shales, you're getting an average of all the stuff that's coming off. We find shales themselves exposed on land, like where I grew up. The house I lived in was built on a big section of shale. So I used to go out as a kid all the time because you could, hit it with a rock and break it apart, find little fossils and stuff in it. And so shales are a good, what we call geological averager, because they kind of represent the sum of a bunch of different processes. And none of these rock types come specifically from one of these, right? They come from some combination, some processing. So if we want to know the average composition of the crust, let's just say, well, let's just figure out the relative amount of each one of those rocks and their average concentration and average them together. It's like, there's too much averaging of averaging. So instead, what we do is look at some of these materials that make geological averages. One of them are shales. Another one is something called loess, which is a very, very fine-grained, wind-blown stuff that is formed from the rock flour as glaciers go across the landscape during ice ages. They scrape off rock, they transport, they average, and they deposit. So we'll look at those two things together. And you might say, oh, why do we care about this stuff? Because the two main questions that we have about the continental crust are, has it always been the same? Or is it changing over time? Right? Is it not only compositionally, but is the process through which we're making it changing? Like, is there like a record of pre-plate tectonic oceanic or continental crust and post-plate tectonic? Or, and how does this relate to those growth curves that we showed? And we also want to know, all right, how does the crust relate to when the atmosphere was formed? Okay, and there's things about our atmospheres we'll talk about coming up today that changes in oxidation state because of the evolution of life, which then changes the behavior of all the siderophile elements because the iron changes from being +2 to +3 and a bunch of other stuff like that, if we can set ourselves up with a geological archive that tells us composition of oceanic crust over time, then we can start to relate it to all this other stuff that's happening on Earth and get a picture of how the whole system kind of works together. That's kind of really what we're after. Okay, so the ways we can get the composition of the oceanic crust, there's sort of 3 ways, right? One of them is to just do direct analysis, like send out an army of graduate students all over the world and say, go pick up 10 rocks and bring them back, and we're going get their composition, and we're going to average across millions of rocks, and that's our average. And again, what you would probably find when you do that is most people are going to go to the cool places, right? The places that are fun to visit, and the places that aren't so fun to visit, we're not going to have any rocks from there. So it's not a really good way of doing it. Plus, when you do this, all you get is the stuff that's today up on top, right? You don't get anything that's inside because we don't go down it. Another one is to do this analysis of geological mixtures, the things like shales and loess deposits. This is more integrative than this, but it also is telling us about the surface skin, right? We make sediments up at the top, we make loess up at the top, so it doesn't tell us what's down below. So we have to combine, we make geophysical inferences about the lower and the middle crust. And again, this will be by looking at geophysical properties like how much heat they have in them, their heat flow, and their seismic wave properties, and relating those back to composition. So I'll get to that in a second. But first, we want to talk about this one here, the analysis of geological mixtures. So geological mixtures are composites, and we can date them, and so we can get mixtures from different periods of time. So this is an example from your text of one mixture. This is loess, okay? This windblown, dusty material, very, very fine grain, that's initially produced at the base of glaciers, and as glaciers retreat, the stuff accumulates, gets blown, makes thick sections, and we can sample them. And this is other estimates of continental crust that come from those kinds of calculations that we just went through with the, the various models and so forth. So this shows you kind of, the alignment. There are a few elements that are off the line, the one-to-one line, but many of the elements that we find in loess are very similar to what we find in continental crust. So it's like a little bit of circularity of these arguments, but over time, there's several kind of well-cited, commonly used estimates of what the upper continental crust is made of, right? Taylor McLennan is one of them, and there's a couple of others, and in part is based on this, right? So the fact that they kind of correlate with each other is like I say, it's a little bit circular, but suffice it to say that this is a good archive of the crust. Okay. Now, shales are another geological mixture. So this is just the rare earth elements. It's not everything. Shales are transported through water, right? The sediments get transported through water. So any of the water-soluble elements could be stripped off of those particles. Plus, you remember all the stuff we talked about with particles and estuaries, so all that stuff goes on. The rare earth elements are pretty much not affected by that process. So they're reliable. In loess, which is windblown, where there isn't much water involved or any water involved, we find a better record for other elements too. But the elements that are affected by water can be affected in the formation of shales. So for this example, again from White, he's just using the rare earth elements. Again, they're normalized to chondrite, right? And you can see here that in shales, even the things with the lowest concentration are 10 times as high as chondrites, right? Which gives us the idea that the continental crust is 10 times as rich in the things, these kind of mildly incompatible elements, as the mantle that it came from. The highly incompatible or lighter rare earths are enriched by about a factor of 100. Okay, and these are averages. And so you can see here some different things. This is one group's composite of North American shale. Here's another composite of European shale. And the third one is basically this early estimate of the average continental crust from the arguments that we just went through. And so all three of them come out pretty similar. They're not exactly the same, but they all show a little anomaly at europium, our element that behaves a little bit differently. They all show a pretty flat pattern in what we call the middle to heavy rare earths, which is basically just this half over here from europium over. And they all show the same amount of light rare earth element enrichment. The lighter the rare earth, the more enriched it is. Okay. So now let's look at another kind of compilation that goes beyond the rare earth elements to include all the others. Okay, this is based on several things. It's based on the original estimates in these guys. This paper here basically took that stuff and added to it information from shale and information from losses, and they're compared with each other on this diagram. Again, normalized. In this case, instead of the chondrites, the primitive mantle. For many of the elements, there's the only difference between the primitive mantle normalizing factor and the chondritic factor is the core. Like, is the core in that mass or not? And basically, we all have values. Everyone kind of agrees in the sciences, in this case, to use the same values. You cite what you're using for normalization, but these are things like you can just pull them down off the web, and then you can do these calculations yourself as well. Because if we were normalizing each of these things with different normalizers, then they could look different. But so this is other people's published data. This is this original estimate. This is this other estimate. And to the untrained eye, they look basically the same, right? There are some subtle differences, right? Like these guys in red or brick colored, as well as others in the literature, kind of reevaluated and said, yeah, you know, we think these very lightest rare earth elements are a little bit higher than Taylor and McLennan said. We all see, you know, europium anomaly. We see cerium anomaly, which is something we will talk about later. It's another rare earth element that has a slightly different oxidation state. There's a big spike at lead. There's some features on here that we will talk about when we talk about the igneous processes that form this pattern. But for now, I just want you to get the idea that when we look at the full range of incompatible elements, which has here the rare earth elements plus stuff that's more incompatible, right? So cesium, rubidium, barium, thorium, uranium, potassium, niobium, these are all more incompatible than the most incompatible rare earth element, which is here, lanthanum. These are written in their order of incompatibility from most to least. So in general, if you look at the periodic chart, these guys over here, plus thorium and uranium are more incompatible than lanthanum. But lanthanum is pretty incompatible. It's just that these are what we call the highly incompatible elements. And so they happen to be even more enriched. So that's kind of how you make the upper crust. And you can compare that upper crust composition with what do we find at island arcs, okay? Island arcs, subduction zone processes, interoceanic. This happens to be compositions from the Banda Arc, which is one section of Indonesia, kind of the central portion of Indonesia. Comparing the composition, average composition of rocks collected there with the estimates for the oceanic crust. So this is the rocks from the arc, and the gray band is the rocks, the kind of average of those values on the last chart. And you see it again, those patterns look pretty similar. Not exact, pretty similar, but they've got these really interesting compositional anomalies, such as a big spike in lead and these depletions in a relative sense. And again, these are normalized concentrations in niobium and tantalum. There's no other igneous province on the planet that has this kind of thing. Mid-ocean ridges, Hawaii, intercontinental volcanism. Only island arcs show this signature, which gives us the idea, and there are other independent lines of reasoning for this as well, that the process through which continental crust is formed somehow happens at subduction. Okay, it's not an exact match. There are some complications here, and not all continental crust looks like andesites that come from subduction zones, but it's the only primary magmatic province on Earth where we make stuff that to a first order looks like continental crust in its trace element patterns. So this is part of how, so that again, it comes back to this question about when did plate tectonics start on the planet? And if plate tectonics didn't start until about 3 billion years ago, meaning we had 1.5 billion years of Earth history without it, however did we make continental crust? Well, we must have made it by some other process. And maybe that crust was different in the early days. Maybe that crust was more like the Venusian and the Martian crust, lower density and maybe a little bit less mafic. And we have not so much of that stuff left that we can say that it was like a clean break or a transition, but we do have the idea that when we go back in time, at some point we didn't have plate tectonics and we must have made crust a different way, just like the way we make crust on other planetary bodies. Okay, so what about the rest of the crust? That's the upper part of the crust, the part that we can sample. What about the middle crust and the lower crust? If we assume that the lower crust is made out of the same stuff as the upper crust, then we have some problems with that. The crustal density we calculate is way too low. The composition is too enriched in lithophiles, like too much stuff stripped off of the mantle to explain the compositions that we see in mid-ocean ridge basalts, which are coming from the mantle of the strip. And it has too much thorium and uranium and potassium in it, so that would give us too high of a heat flow. So based on these 3 lines of evidence, we think that the lower part of the crust isn't as enriched in all these goodies, all these incompatible elements, as the upper part. The upper part, which we can directly sample, the lower part we can't. So the way we make these kind of inferences of what it is there are places where we can find really deep rocks. Like for instance, exposed in the San Gabriel Mountains, which form the northern boundary of Los Angeles, which is one of the 2 fastest rising mountain ranges on the planet, the other being the Himalayas. There are some rocks in what's called an anorthosite belt that formed close to the Moho. Really deep rocks that, because of kind of faulting and tectonism, have been brought up to the surface. We can look at them. We have these all over the world, but they're rare. They're few and far between, and for all we know, they're all in something anomalous about it. So the main way that we do this is by seismic interrogation, because seismic waves, they're seismic networks all over the planet. We can look at how fast waves travel through different bits of crust and relate that to a combination of what is the crust made of and how hot is it. And we take those 2 things plus measurements in the lab that try and correlate seismic properties to different rock compositions, like people make these measurements, and then we try to piece together a logical composition for the lower crust based on the seismicity patterns, as well as some of these inferences that are made by the laboratory studies. And so again, they're not perfect, but they work okay. So this is a diagram showing you seismic velocities, how fast seismic waves propagate in 4 different velocities. Higher velocity usually means, denser mantle. And I mean, so even though temperature is always increasing as we go down from the geothermal gradient, the pressure is also increasing. So we have to think about a combination of factors. There's also mineralogic phase changes into minerals that are better at propagating seismic waves. So we always see seismic velocities increase as we go down. It's a question of how fast do they increase. If you go down in the crust in a place where it's really cold and down in the crust in a place where it's really fast, you will see a greater increase where it's cold and a lesser increase in velocity when it's warm. And so from this model, looking at crust from a bunch of different places, the oldest parts of the continents, the shields, which we talked about last time, we go to subduction zones. We can go to places where the plate is starting to rift apart. When we look at the seismic structure, we see some subtle differences, but some general similarities. We've always got an orange band below a gray band, below a white band, and the thickness of these bands vary a little bit from place to place. The proportions vary from place to place, but there's a structure there that implies that the upper crust, the middle crust, and the lower crust might have different compositions, right? And the only one that's a little bit different from all these, this one here, the oldest, coldest parts of the continents, the shields, which we talked about last time, they, in their upper cratonic part, this is part of what makes them so stable and why they don't resubduct, is that they have slightly higher seismic velocities than the stuff beneath them. Pretty much everywhere else just increases on the way down, because this crust, in a relative sense, is all much younger, geologically warmer. Okay, so now these are some lab measurements that look at the velocity of P waves, one of the 2 types of seismic waves, the pressure waves, through various rocks as a function of how much silicon they have. And you can see an inverse correlation. It's not an awesome correlation. There's a lot of variation because there's other things about rocks that can affect this, like the texture and the size of the minerals and all that. But into a first order, you can use this variation to take the data on this thing, right, and estimate from the seismic velocities how much silicon we think is in that rock. And then we can apply the same kinds of reasoning that we just went through with making melt and transporting it off the melt to kind of calculate an approximate silicon concentration and then we can also use the heat flow that comes off of it to estimate the thorium and uranium and potassium, because they're our main heat generating elements. And with those 2 things and comparing ratios of those to other rocks that we can pick up, we can make some guesstimates of what the lower mantle, the lower crust looks like. And when we do that, we come up with these kinds of patterns. So again, this is normalized concentration to chondrites, and it gives you an estimate for the upper crust, which is kind of like what we've already been looking at, the middle crust and the lower crust, just by taking that relationship I just showed you, as well as the thorium, uranium, and potassium relationship, and how all the rare earths vary relative to that. This is another comparison where we're basically looking at the ratio. Now we're normalizing not to chondrites, but to upper crust, right? So this is what the lower and middle crust would look like when normalized to upper crust. And what we find is that the lower and middle crust have more of the compatible elements and less of the incompatible elements, right? So it tells us it's not all the same stuff, if that makes sense. And so we can use these inventories, and we'll talk about them again more, but I want to spend the rest of the time now talking about the evolution of the atmosphere and how that corresponds with the formation of crust. So we kind of have these various questions, you know, hopefully, if you're interested in your sciences, you have these questions. When did the fossils come out of the silicate earth? When did we start to make an atmosphere? How has the atmosphere changed over time? And how and when did our present system with an atmosphere and a hydrosphere and a hydrologic cycle and all that business, when did it form? And so these are questions that we can ask. We kind of need to know, where did Earth start? Like, what were the gases when we first condensed? How did that change? How did that change during that big impact? How did that change when the core was formed? And then how did it change when life evolved on Earth? Well, all that stuff are things that we can make some boundary conditions on and calculate. There's just a few things I kind of want to remind you about. Today's atmosphere is mostly nitrogen, which is chemically inert, largely, not 100%, but largely, as we've already talked about. 21% oxygen. It's the only planetary body in any solar system, ours or others, that we think is this, and it's only there because of life, right? It's not thermodynamically stable. We didn't have photosynthesis, we wouldn't have it. And then it's the next most abundant thing, a little bit less than percent, is argon, one of the noble gases. And then we go down to CO2, and then all of the other stuff in much smaller amounts. The atmosphere is stratified, right? It's not the same as it goes up. There are various layers and horizons and different proportions of gas. And in general, as we've talked about before, stuff below the troposphere, the tropopause, which is the troposphere, has different composition than stuff above, okay? Some of the questions that we're really interested in as well, like, where's the liquid water, for instance? The liquid water is pretty much all below the tropopause. It's in the troposphere. If water manages to get above that, it breaks down. We can make some water and break down some water by this reaction in the stratosphere and above, right? But there's a lot less of it. And so instead, we find the components that make up water, the hydrogen and oxygen, involved in other molecules. So this is the structure of the atmosphere. You're not going to memorize the names or anything, but when we're talking about the troposphere and the stratosphere, we're talking about way down here at the bottom, right? So there's a lot of atmosphere up there. And there's this temperature structure, which is basically part of why the water stays below the tropopause. This is a zoom in to this little part down here, okay? What kind of helps define this variation is the ozone layer, which now that is present, and it wasn't always present, you need to have, as we talked about a few weeks ago, you need to have oxygen to make ozone. You don't have oxygen if you don't have photosynthesis. So suffice it to say that before we had photosynthesis on the planet, we didn't have an ozone layer. And we didn't have an ozone layer, the atmosphere was probably structured differently, and more ultraviolet light managed to reach down to the surface. So think again about evolution of life. It's hard to put life on land when you're flooding the surface of the planet with ultraviolet radiation. If you start to have photosynthesis in the oceans, in the water, you start to make oxygen, you start to build up this layer, then all of a sudden there's not so much UV and life can evolve from the oceans onto land. That's why we start to really see the first terrigenous life happening, you know, more like 600 billion years ago, even though we think photosynthesis started about 600 million, I should say, 0.6 billion, whereas photosynthesis started about 3.5 billion years ago. Okay, so this is a composition of the atmosphere. Looking at atmospheric gases, they change in concentration and in absolute value. They get lower and lower. So these are number densities. It's a kind of a funny way of describing concentrations with the number of atoms per volume, cubic centimeter. And, you know, all these things that are parallel to each other are gases that are not very reactive, things like the rare gases. And once we get above, significantly above the tropopause, we find more atoms, like oxygen atoms, which are radicals, helium atoms, hydrogen atoms, etc. And lower down, we find more molecules, right? Stuff that's stuck together. It's just too energetic up here for to have much molecules. But we know what we have now we have some estimates of what we started with, and we want to know how do we get from that place to this condition. Is it happening in one step? And the short answer is no, it took many, many steps. So if we think about the atmosphere initially, it reflects condensation sequence, right? How our distance from the sun, what was there in the atmosphere. And so we start with that, and then we start to build up our dust particles and our planetesimals, and they're colliding with each other. The sun early on has a superluminous phase, which is helping to push out some of the lightest gases. That's why they accrete more to Jupiter and Saturn and stuff. So we're already kind of stripping away our hydrogen and our helium relative to some of our heavier gases. But then we start to build up the planet, and we're getting all this heavy bombardment. We're starting to melt all over the surface. It's getting hot enough that, like, for instance, when we make the moon, we know that we volatilize some potassium and maybe even some silicon. So it's a fair guess that a lot of the things that are even more volatile were put back out into space and maybe didn't stay with the planet, right? We may have lost some early gases. Then things start to settle down a little bit. The bombardment ends. We start to do more life. We're making continental crust. We've segregated the core, and we're getting into a more stable igneous process. There were additional gases that were stored in those rocks that started to come out. Like even today, you go to Kilauea volcano, there's carbon dioxide coming out, there's sulfur coming out. That's not coming from nowhere. That's coming from the rock in the mantle that was melting to produce it. So it's always coming out. And so the question is how much of our atmosphere that we see around us was produced by that process versus stuff that came with it initially early on. And then, as I've mentioned now several times, the evolution of life has changed. Not only do we or not have oxygen, but the oxidation state of everything else, right? How oxidized or reduced is the carbon and the nitrogen in the presence of different proportions of oxygen and hydrogen. And so all of these things are, kind of part of the estimate. So we can make some calculations, really simple calculations based on the solar abundances of elements, the condensation sequence, and the fact that we know we lost most of our hydrogen and our helium, to say stuff like, okay, so for instance, for these chemical elements which are important in life, right, the carbon and the hydrogen, what oxidation state were they formed in? And there's a couple of things that we can calculate just using thermodynamics, such as the relative proportion of carbon that is as methane or CO2 as we change the partial pressure of hydrogen, right? And so partial pressure of hydrogen of 1 would mean our atmosphere has 1 for partial pressure now. 100% hydrogen atmosphere down to 10 to the minus 8, because that's a log scale. And so you can see where the switchover happens, right? You have to get down to pretty low hydrogen to not have this. And so the question is, well, when did that happen? How early did we lose our hydrogen? We know we started out with higher hydrogen at some point. And so there was probably a mixture of these two things, right? Another thing we can ask is, in the presence of certain amounts of hydrogen, what's the nitrogen like, right? And again, when we have an atmosphere that's really rich in hydrogen, we make a lot of ammonia. And as the hydrogen goes down, we make less and less ammonia. So these are important considerations on, because ammonia is a lot more reactive than nitrogen. If we're going to start to generate life on a planet, you kind of want to know this stuff. So another way we can get at this, like, well, how much hydrogen was present, is by looking at the redox condition, the oxidation state. And the oxidation state is defined by several what we call buffers, sets of minerals that when they are present together and they are melted, they allow a certain fugacity, which is a high pressure equivalent of pressure, to be produced. And so just like anywhere else that we talked about the hydrologic cycle and everything else on PE, pH diagram, we can calculate basically the PE of the environment. And one of the common values for poisoning, remember poisoning is like buffering for PE, is something called the QFI, quartz phthalate iron. Quartz is a mineral, silicon, right, dioxide. Phthalate is an iron-rich olivine iron, molten iron. So this might be an assemblage of minerals at equilibrium that were common when the core was being formed, for instance, and they give us a certain value of oxidation state. There's another one called QFM, which stands for quartz phthalate magnetite. These two minerals are the same, but magnetite now is an iron oxide. It's not as reducing. Okay, and so when we take an assemblage of minerals these two minerals and we change the temperature on them, right, we will get a concentration of oxygen. These are really low, right? This is the log concentration, 10 to the minus 15. Very little oxygen present, but it's an oxygen fugacity, right? And availability of an electrons. We can plot out what that is as a function of temperature, okay? And know if we make igneous rock to this temperature or that temperature or that temperature, this is what the fugacity is going to be. And so, like I say, we've got, somehow my blue box got deleted up here. We've got a blue one and we've got a red one. And for each of these two conditions, we can take all the gases that we find in our atmosphere and we can calculate on a basis of their presumed abundance from the solar abundances, as well as these two buffers, what are the relative proportions of each of these gases. Okay. And so I've kind of zoomed in on that here. And these two proportions allow us to estimate the relative amounts of the gases which are here. And so you can see, for instance, at the more reducing one, there's more hydrogen and less water. And in the more oxidizing one, there's more water and less hydrogen. You can look at the relative proportion of carbon dioxide, carbon monoxide, sulfur dioxide, hydrogen sulfide. They all vary as a function of how oxidized or reduced stuff was. Okay. So I've got some calculations here. I'm not going to try and go through in class, but basically, how do we get the data in that table? We make a couple of assumptions, like the carbon-hydrogen ratio. We assume one partial pressure of atmosphere. We pick a temperature, right? And then we have to solve a bunch of equations simultaneously. We got 5 unknowns. We want to know how much hydrogen, how much water, how much carbon dioxide, how much CO2, and how much oxygen was present. Solve those simultaneously. It's done here, and that's basically how you come up with the results that are in that table. I just want to get through a couple more things, and I'm going to leave the rest for you to read, which is that basically after that early atmosphere formed, the next few things that happened were bombardment and loss of a proto-atmosphere, and then the development of life. Okay, both of those things are described in here. And the evidence for them is described in here. And, in the next handful of slides, I guess I'll try to summarize them at the beginning of next time. I mean, I think everyone knows what the story of the evolution of life is, but I have some data in there about things that change as the atmosphere becomes oxidized that we see in the rock record. Things like the concentration of sulfur in its form and iron and everything else. And we'll also talk a little bit about how we know that Earth lost its early atmosphere. It was completely blown off, and that what we have on the planet is what's called the stage 2 atmosphere. The early atmosphere that we created with Don Johnson, and then Earth starts doing its thing that makes a new atmosphere. That new atmosphere has evolved over time because of life, but we lost most of our early volatiles. Maybe in that moon forming event, maybe before that, or maybe during it, or whatever. All right. Are there questions about that? Did I record?